Hey grade 12s, I am just going to go through the calculus notes that you've been given over the past week or so. This is a really new sort of math language, so to speak, and I know it's quite confusing to a lot of you, so I'm just going to quickly go through the notes and hopefully just make you feel a bit better about this chapter. Okay, so you've been given these notes bit by bit over the past while. I'm just talking through the first page or so. We started talking in this chapter about limits. We spoke about limits when we spoke about the sum to infinity of a geometric sequence where it was heading towards a certain number, but it would never get to that number. Okay, that's the concept of limits. In this 1.1 and 1.2, firstly 1.1, there's no real limit here because you would have seen that whatever I put in for the x value, I always added to. So you were never heading towards a certain value. However, in 1.2 here, because your denominator could result in having a 0 when x was 2 over there, you would have had an undefined answer. So from the left, as you subbed in values into your x's up until just before 2, your answers for fx was getting closer and closer to a certain number. Same as if I substituted in from the right, my answers were getting closer and closer to a certain number. That is my limit. And you would have seen in this question that it was getting closer and closer to the number 4. Okay, it gets closer and closer to 4 without having 0 as its denominator because it will be undefined. Okay, so you work through these little discussion here, and hopefully you would have seen what it was talking about in terms of limits. The table method up top in 1.1 and 1.2 is doable, but it takes a long time. So they said, either use the tables as in 1.2 or simplify the expression as follows. So this is the notation, and it's very important how we write it. It writes here, limit as x heads towards being 2. So if you simply sub in 2 here, you're going to have an issue at the bottom because you're going to have 0, and that's going to cause problems. However, if you factorize the numerator as x plus 2, x minus 2, difference of 2 squares, you're then able to cancel your x minus 2's, and you're left with the limit as x heads to 2 of x plus 2. Now, when I sub 2 into x over there, 2 plus 2 will give us the limit of 4. Okay? The table up top is option 1. Option 2 is just to simplify and factorize. Okay? Your page 2, or you didn't have page numbers, but your next page spoke about doing tables, but also using the simplify method. So in number 1, you would have seen that this limit here, and I added it in my notes, when x was 0, your limit was heading towards what? From the left, you could see it was getting towards negative 2. From the right, you could see it was getting towards negative 2. Our answer is confirmed to us. If I had cancelled my brackets there, I would have had x minus 1. Now, when I sub in negative 1 in there, negative 1 minus another 1 is negative 2. So both the cancelling away method and the table method confirms our answer to be negative 2. Okay, you did several of these table methods, okay, which you're never really going to do in exams and that, but hopefully it just gave you the idea of where we're heading. Ending off with number 4 here, your last table one said, what's the limit here as x heads to 3? Once again, if I put 3 at the denominator, I'm going to have issues. So I use quadratic trinomial in the numerator. I cancel my brackets. I have the limit as x heads to 3 of x plus 1, which is 3 plus 1. Now our limit is 4. The table confirms it to us as we approached from the left. Our answers were getting closer to 4, even though it was undefined here. And from the right, it was getting closer and closer to 4. So our answer for our limit here is 4. 5, 6, 7, 8. We had a similar story here. You could not just make that naught because it would be divided by naught. So I cancelled. I had 2x squared. Now I subbed in the 0, and then my answer, my limit down here, you would have seen, would have headed to naught anyway. Right? Over there, answer naught. Number 6, if I subbed in 10 there 3 times, 20 is 60. There it is, 60. The limit as h heads to naught here. Simply, if I subbed in naught there, our answer left over would have been 3. Number 8, if I subbed in 3 there, 5 times 3 squared plus 1, all would have given me a limit of 46. Okay, 9 that gave you, Mr. Norman gave you the answers to these a while back, is a complicated one, and look carefully, I'll go through it quickly. It said, given that the sum of a certain number, 1 plus x squared plus blah, 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 you can see that this is a geometric series where our R value is x. Okay, so in 9.1, it says, show that all that. In other words, the sum of 5 of these terms. So I go down to my old sum formula for a geometric. Sn is equal to a 1 minus r to the n over 1 minus r. So if we want the sum of 5, it's 1 brackets 1 minus x to the 5. You remember x was the value of our r and a was 1 there, 1 over 1 minus x. I then times that denominator to my left side, and I've got 1 minus x times s to 5, and I've got what they wanted us to get. Okay, 9.2 then stepped it up a level and said calculate the limits as x heads to 1 of that. Okay, my answer's on the right page here for some reason. You would have seen here by my answers, and hopefully it comes out clearly, that as the limit heads, or as x heads to 1 of there's my question, I take 1 minus x, 1 plus x squared. That was the whole difference of cubes, a way of factorizing. And then 1 minus x to the power 5 was what our right-hand side was equal to over there. So I'm going to bring my whole left-hand side there, and I'm going to put it as my denominator in 9.2 over there. Great. So now I can cancel my 1 minus x's. Okay. Then I'm left with the numerator is 1 plus x squared. The denominator, sum of 5, is simply, I've expanded, yeah, roughly, maybe you can figure it out, hopefully, 1 plus x squared plus x cubed plus x4. Okay, I've just subbed in. Now when I sub in my limit that x is heading to, as x approaches 1, I've subbed in 1s for all my x's. And my answer is 3 over 5. Okay, that's the limit it heads to. Carrying on here, it spoke about average versus instantaneous speed, which for those of you doing science may have heard of this before. And it spoke about the distance in meters. It gave a little story here. Remember, this here is pretty much the gradient formula, change in s over change in t. So as they worked out the average speed between 2 points, between 1 and 3, between 1 and 4, 1 and 3, 1 and 2, so the change in time, the denominator got smaller and smaller, right? So my average speed of 25 meters per second, 20 meters per second, 15 meters per second, 10,5 meters per second, and so on. Do you notice that my denominator was getting smaller each time, right? That's because the comparison between t of 1, let's say, and t of 1, 1 is only 0,1. In the next line, it's 0,01. In the next line, it's 0,001. So as the change in t, our denominator, was getting closer to 0, so my average speed was getting closer to what? To 10. And 10 meters per second would then be described as our instantaneous speed, not average. Okay, but can it ever be equal to 0? No, because then you're going to have divided by 0 and it's going to cause issues. So you can once again either go with tables to work out the instantaneous speed, or you're going to work out, there's the table I speak of there. Okay, you would have seen there that as our change in speed was getting closer and closer to 0, so was my speed getting closer and closer to 10 meters per second. Okay, instantaneous speed, it tells you, is defined by the limit as the change in time heads towards 0. We've discovered that in our activity we just looked at. Okay, then we got to this formula, right? The change in distance, this is here, hence the average speed is given by the change in distance over the change in time. Great, that's what we worked out on the previous page. So f of 5 plus h minus f of 5 talks about the, if your original f of 5 is your time after 5, a plus h means a little bit further on from your 5 position, just a little h away, over h being the change in time, the little bit away from 5. Okay, So to find the instantaneous speed at, and that's the important little word there, at 5 seconds or at the 5th second, it was necessary to consider what happens as h approaches 0. As h approaches 0, f of 5 plus h minus f of 5 over h. You have worked that out in your table up earlier, and hopefully that just helps a little bit. Okay, this can be confusing, but it does get easier when we work with now the next section. Gradients of chords and tangents to curves. Very important here. I'm going to go through this fairly quickly, so pause it if you need to. Results similar to the above are obtained by considering the rate of change of any function. So straight lines, parabolas, hyperbolas, all sorts. Value fx in relation to the change in x. So here's an example. If x is equal to 5x squared, so what is that? It's a parabola. The average rate of change in fx as x changes from 5 to 1 is given by the gradient of the chord joining 1 and 5. How did I get that coordinate? If I subbed 1 into x, I would have got 5 for my y. And if I subbed in 5 over there, I would have got 125 for y. Okay, so the average rate of change between those 2 points will be given by the gradient of the line joining those 2 points. Okay, so on the next page it says the average rate of change, there we go, is equal to the gradient of that chord. There's my gradient formula, change in y over change in x. So 125 minus 5 over change in x, 5 minus 1, is 30. So that is a very steep gradient between those 2 points. Okay, and let's say they are, yes, they are those 2 points there. Between A and B, it's a steep gradient of 30. The instantaneous rate of change at the point where x is equal to 1 is given by the gradient of the tangent to the curve at that point. In other words, the gradient of that line will tell you the instantaneous rate of change at that point A, where x is 1. Okay? So this whole table that follows tells you that as your line segment there, as A to B1, okay, A to B1 became A to B2, became smaller and smaller and smaller. Eventually it became the tangent, right? What is happening to the gradient of that line? That's what this whole table is discovering for you. You would notice that there is a limit kind of being discovered in this table. Do you see that? Where I've got my little arrow there and there. When x is 1, right? Because you remember we're comparing everything with our original a, which is 1 and 5. So when x was 3, right, we're going to compare that point with the original a, 1 and 5. However, here, there's a little number here that's missing, I guess. When x was 1, it would have caused issues because the change in y over change in x would have resulted with a 0 at the denominator. But you could see that the gradient, as your line segment was changing, your gradient went from 30, the one we worked out earlier up top, then to 20, then to 15, then to 10,5, 10,05, 10,005. You'll see that our gradient is heading towards what? Likewise, when we compared with x values from 0 to 0,5 to 0,9 to 0,999 heading towards 1, what was the gradient heading towards? Right? You'll see here, what does the gradient of the curve at 1, 5 appear to be? It's 10. Right? There we go. But we don't usually have a gradient at a point. That would then be the gradient of the tangent at the point. Okay? So hopefully that little discussion assists you with that table. Right. The next page said, a quicker way of finding the gradients of this function that we've just worked out at x equals 1, instead of doing the table method, which just takes forever, is to use the knowledge gained of limits, right? Let h represent a small change in x. Note that h can be positive or negative, yes. The change in y is then given by f of 1, remember a's position was at 1, f of 1 plus a little bit minus the original f of 1. If that is the small change, to work out the gradient then, we then would have to divide by the small change h, which we've given, which we've proposed. So, the limit, as the change in x, the denominator, heads to naught, of the change in y over change in x, remember the gradient formula, is equal to, here we go, the change, or as h approaches 0 there, of f of 1 plus h, the small little extra bit, minus f of 1. We've taken that and we've put it into a gradient formula. Okay? So now, this is a generic formula. It has nothing to do with our actual formula of 5x squared. Right? So now, calculating the gradient at x of 1 for this function, right? Here's our notation. This f dash or f prime or whatever, first derivative is actually what it's referring to, but we'll get to that just now. F of 1, f dash 1, is h approaches 0 of what? 5x plus h, right? Instead of just 5x squared, we've got 5 of 1 plus h. We got that from earlier. It's an h away from 1, okay? All squared, because we had a square in our parabola, minus 5 of 1 squared, okay? That formula just customized for the function we've got, 5x squared, over h. Now we just simplify a bit. So 1 plus h all squared is 1 plus 2h plus h squared. We times the 5 in, and this is just simply leaving us with minus 5. We'll note that the 5 minus 5 cancels each other out, and now we can take out, I added a little step of workings here, I could take out an h as an HCF and cancel the denominator h with my HCF. So what have I got left? 10 plus 5h. Now when h approaches 0 there, so that approaches 0, that whole term, and our limit that we are heading to is 10. There it is. And what did we find from our previous page? It was heading to 10 there as well, from the table method. Okay, so this here is the way we're going to go by using this long sort of formula. Okay, so we then had the questions that followed. 1, 2, 3, 4, 5, 6, 7. I think you may have even had another one, and you went through them gradually. I'm just going to do maybe 1 or 2 of them with you and end this video. So for number 1, what did it says here, firstly, now apply the above method to find the gradient of the tangent to the curves at the given points. So for 1, y is equal to x squared, we've got a parabola, and we want the gradient of the tangent to this parabola at 2. Okay, you could think, if you wanted to draw it, you could have your parabola there, like so, and then add 1, 2. What is the gradient of that line when x is 2? That's what we are after. So remember, we use this notation, right? The limit as h approaches naught of what? We want it at 2. So 2 plus h, okay, because we wanted the limit as h approaches naught, so we add a little bit extra, a little h, a small change, minus the 2, all squared, because the value is x squared. You see there? So instead of x over here, you've got 2 plus h, and there you've just got a 2. 2 squared is 4 plus 4h plus h squared, so you've FOILed out that bracket, minus the 4. The 4's cancel. I take out an HCF. I cancel the h's. I've got h plus 4. Now that my h approaches naught, naught plus 4, my answer is 4. Happy? Number 2 gave you a straight line, so you would have done the same thing in my answer here. You'll see 5x minus 2, but instead of an x, I've got minus 1 plus h. 5x minus 2, but instead of an x, I've got minus 1. I've bracketed that whole thing because I'm subtracting the whole thing. Okay? Please make sure you do that. Right? Over h. Right? Now I just times in, I simplify, I get 5h over h. I could cancel the h's, and my limit is 5. Right? Number 3, it gave you x squared plus 3x minus 2. So it's also a parabola, but it's just written in a different format. at x of negative 2. So instead of having just an x, you're going to have an x plus h, first of all, right? Here it is, x squared plus 3x minus 2. But instead of an x, you've got negative 2 plus h, negative 2 plus h, right? And then minus the whole thing again, but now there's no h here, there's just the negative 2, and we are all over h. Okay, so we now FOIL that out, we times in there, we times that out, and we get that numerator there over h, which simplifies to h squared minus h over h. I can take out an HCF of an h. I can cancel the h's, and I'm left with h minus 1. Now, when my limit goes to h of negative 2 minus 1 is negative 2 plus 1 is negative 1. Okay, is that right? Negative 2 minus 1 is negative 3. Is that right? Negative 3. Let me just check here quickly. Yeah, no, that is right. Negative 1. Okay. Right, so let me do one more. Let's do the last one here. Let's do number 5. Number 5, y is equal to x cubed. Okay, now we're dealing with a cubic graph, which we're going to get to soon, at x is equal to negative 1. So they give you the answer of 3. So I've got my answer scribbled in here in the bottom corner. The limit as h approaches 0 of not just x cubed, it's negative 1 plus h cubed, minus, not x now, negative 1. We've got our value. That all cubed, if I, quite small there, if I times that out, I get h cubed minus 3h squared plus 3h, and then I minus, minus of a minus 1 gives me my little plus 1 up top there, you see. So there's my numerator. I take out an HCF of h, I can cancel with the denominator, and I get h squared minus 3h plus h. Now, as my h approaches 0, those two fall away, and my limit there is 3. Okay, so hopefully going through these last few pages of your calculus notes has assisted you, just getting you ready. We are now going to head to the new page, which would have been sent out, I think, on Friday. I'm going to go through this page here, the derivative, and I think this was sent out this morning, so I'll also talk to that shortly.